We'll continue where we left in the introduction chapter. Stress and strength. Okay, so when we talk about stress, we usually mean an engineering quantity which is defined as force per unit area. Okay, and when we in case of engineering materials, stress is the force per unit area at a certain point, okay, at a specific point on the body or in the body. Okay, and stress depends on various factors, including the load, the geometry, the temperature, the manufacturing process used.
Depends on those things.
Yeah, so if you put if you stress the material and then if you change the temperature of the material, then all those things. You mean the on?
Yeah, okay. That just like I'm trying to grab it.
Okay, problem.
Do we have a run?
Yeah, just let me know if I'm doing anything wrong, and I'll happy to correct it. So the way we denote stress is by this Greek letter. It's called sigma, and sigma is used typically for what we call as the normal stress. Okay, normal stress is a stress which is normal to a surface, and there's a lot of material we'll be covering on normal stress, so don't worry about it for now. We could also denote stress as sigma, tau, and tau here is used for shear stress. Okay, so what does this really mean? Well, if you have an object, let's take a cuboid, and if you subject it to a normal force, so force on the top face, then that force will induce a stress, which is the normal stress, and it's shown as I have in the figure. On the same surface, if you apply a force which is along the surface, then you would have a shear force, and that shear force would produce a shear stress denoted by tau. And then as we learn more, we'll see that we will have something called the principal stress. Okay, that will be in the chapter when we talk about Mohr circle. Then people like to have, in some cases when non-Cartesian coordinates are important, we would have a radial stress. And so on. So the shear stress, when we have a Cartesian frame, we would have tau xy, which is the shear stress in the xy plane. So a lot of machine design or design in general is about figuring out stresses at different points. And wherever the stress reaches a critical value, that's the point which is most important. And that's how you will design a body so that the stress doesn't really reach the limits posed by the material at any point. And that's one of the things we'll be covering in this course a lot. Stresses are going to be an integral part of this course. So what is strength? Okay, strength is we associate when we can lift a larger weight, we say we have more strength than we can lift a smaller weight, that is assuming you're doing some weightlifting. So strength, unlike stress, well, the commonality with stress is that it is also defined as force per unit area, but it's for the body as a representative. So when you say an individual has a high strength, it probably means that he or she can lift more weight than somebody else. So again, the units are force per unit area. And it's for a body as a whole. Okay, and so we'll have what is known as yield strength, which we'll cover a little bit later in the next chapter. We'll have fracture strength and so on. Fracture strength is more advanced. We will not be covering fracture strength in this course, but fracture is important, especially for materials which can break. And usually for thin materials, they usually break by fracture. Okay, now what does strength depend on? Well, strength depends on things like material for sure, the processing of the material, or in this case, manufacturing. So faulty manufacturing can decrease the strength of the same material, so on. So when we talk about material failure, we will typically say that for the material to not fail, the stress at a critical location should not exceed the strength. Okay, so that's usually how they are connected. But remember that strength is an absolute quantity for the whole body, but stress is for a specific location. So for a product to survive or not fail, the stress at all locations should not exceed the strength. Okay, let's move on to the next concept, and that is the factor of safety and design factor. We'll denote design factor by N subscript D, and we also have a term called factor of safety. And we'll use the small n to denote factor of safety. Now, it turns out that both these quantities have the same definition. So the formula for ND or N is the same. It's basically the strength divided by allowable stress. Okay, so the strength will typically denote, and I forgot to put it in the previous page, by S, and then stress, we either have sigma or tau, right? If you're looking at something which is stressed with a normal stress force, which is normal to a surface, we have normal stress, sigma, or we have tau for shear stress. Okay, so how can we have two names for the same thing? Well, it turns out that when you compute the design factor of safety, you actually will end up with two numbers because those two things are used in two different ways. So this is how you can distinguish between them. ND is computed before design is complete, and N, which is the factor of safety, is computed after the design is completed. Okay, and why would the design change? I mean, why would the factor of safety change when the design changes? It turns out that when you use the design factor to compute the stress and compute the dimensions of the object, you go through the catalogs, you may see that you may not be able to get the required dimensions for that particular computation you did. So if you get a diameter of 0.33, say, then 0.33 is something you cannot buy. So then you'll have to shift and buy something which is available in the market, which is probably a shaft of 0.3 or 0.35, in which case, when you use that for the computation of so you do the design, you finish your design, and then when you compute the factor of safety, you will see that your number for factor of safety would have changed, and which will not be the same as the design factor. So I'll do a computation which will make this clear. So let me just quickly put the reason here. The reason they are different is because the dimensions after design is completed, dimensions may change after the design is completed. Okay, so let's illustrate this with a simple problem. Yeah. What's that?
People are in the chat.
Oh yeah, so actually this was happening in the background. I asked them if they could hear me, and then all of them said they could hear me. So yeah, thanks for pointing that out. Though I have another computer, so I'm keeping a track, but I'm sure it's going to be overwhelming very quickly because I'm also have my notes here. Yeah, thanks for seeing that. We have 16 people online. Okay, so that means probably 40 here, but probably not 40. Okay. Okay, so here is a problem, and I don't know if you want to copy this, but as I said, I'll be available later. Okay, so a mechanical system requires a shaft. The shaft is subject to a normal force of 10 newtons. The shaft material is strength of 2000 Newton per meter square. The safety factor is 2, and that's a choice which the designer makes. Okay. So typically, if you want to look at structures which you want to be lightweight, you want to have a low factor of safety, like aerospace structures typically would have like a factor of safety of 2 or 3. And then if you want to have structures where weight is not important, usually immobile things like bridges, you'll have a higher factor of safety. What the factor of safety basically does is, the bigger the factor of safety, the heavier is your design. And so heavier is your design, then, I mean, if you can't have a very heavy car, for example, it just not move, right? Or for that matter, a plane. But if you have a higher factor of safety, what say for a bridge, it's not moving anyway, so it's fine. Okay, so let's try. The point of this question is to just illustrate the two concept facts. The safety factor. Sorry, that should be design factor. Yeah, correct. Okay, so as I said, the design factor is specified by uh, the customer, the client. Okay, so let's go ahead and solve this. Okay, so first of all, let's put it in things we know about. ND is 2. The strength is 2000. And then let's use the formula, which is basically ND is, which is the design factor, is the the strength divided by the normal or shear stress, in this case, normal strength. So we have Q equals 2000 divided by sigma. Then we have sigma equals 1000. So we've got the stress. Now the stress, the definition of stress, and maybe I should draw this. Here, the picture you can think of is this basically a shaft with a certain diameter. It's subject to a force, and let's call that P. And there's some area here, this cross-section area. And then stress is the force, which is in this case normal force divided by the area, right? And so let's write down the formula for stress, which is P, the force divided by the area. So the force is given to us, it's 10 newtons. I'll put 10. And then let me just write it this way. 1000 equals 10 divided by the area. So the area of cross section, one I've shown you here in the figure, is pi d squared divided by 4, where d is the diameter. Okay, so I need to solve for d, which is basically, I think it is 4 divided by pi 10 divided by 1000 square root. So that comes out to be 0.1128 meters. Okay, and I would write this in millimeters, and I'll tell you why in a bit. So what this says is that if the material has to bear that strength of, well, bear the force of 10 newtons with the strength given, then it needs to be of a diameter 112.8 millimeters. Okay, so once you have that design, you need to go to the catalogs, figure out if you can buy that material. And of that diameter, it turns out that there is another chart in the book. I think this is the table A7 or A17, which basically gives you standard dimensions. Okay, so here the problem is in millimeter. Well, we've solved it in SI units, so we're looking at millimeters, and we need to go through this. These are all diameters, so we need to go through the diameter and see if 112.8, 113 is available. So if you go here, you'll see that unfortunately that's not available. It's basically somewhere here, right here. So either we can buy a 100 millimeter diameter shaft or a 120 millimeter diameter. Now the question is, which one would you choose? What's that? 120. Why? The reason is because so we have stress is P divided by A, which is P divided by pi d squared divided by 4. So we can see that the stress is inversely proportional to the diameter. So bigger the diameter, less the stress. So given a choice between two diameters, you want to choose the bigger diameter, because if you go down to 100, and if you do the calculations, you'll see that your factor of safety will drop below 2. And you don't want the factor of safety to drop below 2. So we'll choose the bigger diameter. Now, the caveat with the bigger diameter is that more diameter, more is the mass, and heavier is your whatever design you create. So that's the caveat of going for a design which is not per your calculation. So let's choose. So from table, I think it's A17 in the book, we choose P equals to 120 mm. Okay, and then let's now go back and do the calculation for the factor of safety. So again, let's compute the stress. That's P divided by A. P is 10, area is pi. The diameter is 120 millimeters, so it's 0.12 meters. And I think that works out to be, so what I got is 884 Newton per meter square. And so, by the way, this was the solution to part A. And maybe it's always a good practice to box your answers. So when we grade it, it's very easy to spot it. So A is that, and then B. Let's compute the factor of safety now. So that's N. So that's strength divided by stress. Strength is 2000. Stress is 884.2. And then if you compute that, it comes out to be 2.26. So N is 2.26. Okay, so here's a case where you started with a factor with a design factor of 2, ended up with a factor of safety of 2.26, and the only reason why I changed was because we couldn't find the shaft of the right diameter based on our computation. So that's why those two numbers are different. Any questions? Yeah, questions.
Do you always choose to go by left sides?
Yeah, because if you let's say that you chose, let's do this aside, okay? So let's say that we chose, I think it's best to actually for me to do this. So what if we chose T equals 100? Okay, so let's say if we did choose a 100 millimeter, let's see what happens. So let's compute the strength. That's P divided by A. So that's 10 divided by pi times 0.1 square. Let's quickly do that calculation. So I get 1273.2. Okay, so let's now compute the the factor of safety. That is, sorry, it's N, it's S divided by sigma. So we have 2000 divided by 1273.2. If you do that calculation, you should get 1.57, which is less than ND, which is 2. So now you've not achieved your objective of designing whatever you're designing with the specification mentioned. So always choose the higher diameter, never the lower diameter. Any other questions? Okay, so moving on to the intro, let's talk a little bit about reliability. Okay, so we often say, talk about reliability. How reliable is this thing? How reliable is a person when somebody makes a statement? And we usually, the way we do it is typically we see how many times, say, reliability of somebody saying truth, talking the truth. We basically find all the number of times somebody has made a statement and figure out how many times he's told the truth, divided by all the times they made a statement, and that gives us the reliability of saying the truth. So it's basically a measure, sort of a probability measure, right? And so in design, the reliability is always defined in terms of, 1 minus P, where P is the probability of failure. So you have two choices. You can either write the probability of success or failure. Failure is more what is used. So once you know something has failed and you quantify the probability, then you just compute the reliability as it not failing. So the probability, as you know, is always between 0 and 1. And by virtue of definition, R, which is the reliability, is always between 0, and 1. Obviously, you want a higher reliability, so P should be as low as possible. So good product will have P as low as possible and R as high as possible, where obviously it cannot be beyond 1. So the P, and the way to compute P is number of failed instances total number of instances. So imagine you're doing an inspection of parts, and in your batch, you inspected 500 parts. Okay, out of 500 parts, 8 parts were defective. So example, an inspection process, inspection of 500 parts. Okay, this is say in a manufacturing or an assembly line, showed that 8 were defective. So in this case, your probability could be, by definition, the number of failed instances divided by all instances, and that number comes out to be 0.016, okay? Which means the reliability is 1 minus P, or it is 0.984, or 98.4%. So what do you think that if you're making cars, for example, and if you see there are 8 defects or 8 defective cars out of 500, would you call that a great, reliable car or not? Probably not, right? So there are standards, and these standards comes from the ISO standard, which I talked about last time. They usually, if you want to meet a standard, the ISO standard, then you require a very low probability of failure and very high reliability, typically 1 in a million or something like that, some really high number of, very low number of failures in all instances. And that's kind of one of the goals of the industrial engineer, to ensure that the reliability is as high as possible. Now, the other caveat is that if you make your system too reliable, right, then you're going to make it more expensive, because maybe you'll have better machinery, you'll have more inspections, you'll procure better parts, and so on. So there is like a, the statistic, well, there is like a decision you got to make in terms of cost. How much can you sacrifice reliability for cost? And that's something which, in this case, example of car manufacturers always do. So it's okay if they had 1 failure in a million, that's acceptable. Because if they make it perfectly, there's nothing called perfectly reliable, but if they make it even more reliable, then probably it's going to be way expensive. So when companies try to meet expectations, they try to meet those ISO expectations in terms of reliability. Now, there are 2 types of systems of interest. Okay, and now we're talking about, let's say there's a manufacturing plant where there is a operation 1, operation 2, operation 3, and so on. So the part goes through machine 1, operation 1, then it goes to machine 2, goes to operation 2, and so on. So this is like a series system. So if you think of the arrow as flow of material, it goes from one box to another box, which means it goes from one machine to another machine, and so on, so in a serial fashion. So let's say that the reliability of each of those machines is R1, R2, R3. Okay, then it can be shown that the reliability, the total reliability of the system in series is R1 times R2 times R3, and so on. Okay, so the reliability in this case is a product of reliabilities. That's very important. So there's other systems where it's typically when there are redundancy in the system, and those are called the parallel systems. Okay, next thing is dimensions and dimensioning and tolerances. So 1.14. Okay, The way you get dimensions is typically when you are told to spec something out, you go to a CAD tool like SolidWorks and Inventor. It will actually show you all the dimensions, and that is the design drawing, and that design drawing is used for manufacturing. So there's some definitions here which are important as design engineers. The nominal size, okay, is the mean or the average size. So what you do is if you have 100 parts, let's say shafts, then you just go and measure the diameter and then take the mean, and that gives you the average size, which is also the nominal size. There are limits, which is the max and the min size. So if you have 100 shafts and you go on measuring them and you find that the mean is say 100 millimeters, and then the maximum is 101 and the minimum is 99.5. So those would be your limits, 100, 101 and 99.5. Tolerance. So it's the difference between the min and the max and min size. Now, in this case, we have two types of tolerances. One is what is they call the bilateral tolerance. Okay, so an example is if you have a shaft of diameter 1.05 millimeters or inches, sorry, then you could have a limits of 0.001, which means that there's a bilateral tolerance. It could be 1.05001 or 1.05 minus 0.01, which is 1.4999. So that's a bilateral tolerance. The tolerance is on both sides of the nominal. Then we have something called a unilateral tolerance. An example would be 1.05, but it only has an upper bound and no lower bound. So 0.000. Okay, two more things. Clearance, or three more things. Clearance. And this is typically used in when you talk about mating between a bolt and a hole. Okay, so if there's a shaft and then there's a hole, and you want to ensure that the shaft goes in the hole because that's what most of the you have screws, you have nuts, and so on. So we're always looking at the external diameter of the shaft and the internal diameter of the hole. And when we have the condition that the diameter of the shaft is less than the internal diameter of the hole, we have what is known as a clearance fit. That is, the shaft will go in the hole. So the opposite to this is what we call interference fit. That's when D1 is greater than D2. And then the final thing here is what is allowance. Which is the minimum clearance or minimum clearance or maximum interference. So it's so-called because when you are talking about a shaft going inside a hole, you don't want to keep too much gap. So you want to have the minimum clearance that but it should still go. The interference in this case maximum because you want to find the maximum limit at which they can get that the interference. Okay, so here is a problem on clearance. And I took this problem in the book. Let's see. So here it is. And I thought it was a little bit confusing the way it was solved in the book. So I'm going to try to solve it my way. Okay, so read through the question. Okay, let's go through this slowly. Okay, so a shouldered screw contains 3 hollow right circular cylindrical parts. Okay, so they looks like this one, and this one. Parts on the screw before the nut is tightened against the shoulder. So this is probably the shoulder. To sustain the function, the gap W must equal or exceed 0.003 inches. The parts in the assembly depicted in figure 1.4 okay, have dimensions and tolerances as follows. Okay, A, B, C, and D. So here's something to note is that the A is basically the length of this screw, right? And these B, C, and D are the parts which go into the screw, like they are holes basically. And when you make this part, so there are 4 parts, right? There's the screw, which is characterized by A. There are 3 parts, B, C, and D. And you can make those parts. And when you assemble the whole thing together, there's a tiny gap between the dimensions. There is certain constraints placed on that dimensions W. Again, there are questions related to that W. Let's see what the questions are. So first of all, gap W must not equal or exceed 0.003. All parts except the part with dimensions D are supplied by a vendor. The part containing the dimension B is made in-house. Okay. Estimate the mean and tolerance on the gap W. Okay, so here we don't really need the information that we need to design it 2.003. Assume that A, B, C, D are the way they are, and we're going to find what the tolerance in W is. So first part is independent of that constraint which is given to us in terms of W should be equal or exceeding 0.003. So let's solve A first. So the mean, okay, so first thing to note is that the A is the sum of B, C, D, and W, right? Just from looking at the figure. Now, if the means have to be, if you want to compute the mean, then the means of each of them should also hold true. So then we can now find W mean as A minus B minus C minus D. And then if you plug in the numbers, where A mean is this, B mean is 0.750, C mean is 0.0120, and D mean is 0.875. Maybe I should just put it 1.75 minus okay, so if you do that, you get 0.005 inch. Okay, so that's the mean. I think the harder part is to estimate the tolerance. Okay, what the tolerance means is it's basically the plus or minus in that calculation. So how do you find that? Now, what I would like to do here is we'll find the maximum and the minimum value of W, which is basically the limits of W. And the way you find the limits is, how will you get the minimum limit on W? What you want to do in this case is, to get the minimum, is you take the minimum of A, take the maximum of B, maximum of C, maximum of D, and that will give you the minimum. So one way to find the minimum is to take A maximum and subtract it from, sorry, A minimum minus B maximum minus C maximum minus D maximum. Okay, are you convinced why that's true? Because the way this is set up, A equals B plus C plus D plus W, when you have the minimum on A and the maximum on B and C, that's when the W would be the minimum. Okay, and so we can find the minimum. It comes out to be, well, what's A minimum? It's basically 1.75 minus 0.003. So 1.75 minus 0.003, and then B maximum would be 0.75 plus 0.001, and then C maximum would be 0.12 plus 0.005, and then D maximum would be 0.875 plus 0.001. So if you do this, you get the minimum, and that comes out to be minus 0.005, which is saying that if the parts are the extreme limits, the way I've computed, then there will be an interference. So there won't be a positive gap, but a negative gap. Okay, so let's compute the other limit, which is W maximum. Now, if to get the maximum on W, we need to go the other way, which is A maximum minus B minimum, C minimum, D minimum. And then if you write this down, which is basically A maximum is 1.75 plus 0.003 minus, and you should put it down though. Choose the minimum limits for B, C, and D, and then what comes out is 0.015. So if you have this kind of situation, then you will have a positive W, which means there's a clearance. So now if you want to find delta W, which is the limits, it's basically the max minus min divided by 2. So that's 0.015 minus 0.05 divided by 2, and that's 0.0.
0.005.
Is that right? Sorry about that. 0.5. So it's 0.01. I think I got the math right here. Yeah. Okay, so which means that the answer for A is W plus or minus delta W is 0.005 plus or minus 0.01 inch. So that's the answer to the first part. What is the tolerance for W? Okay, so the next part, what basic value of B will ensure that W is greater than 0.003? So what it says is that no matter what the situation is, W should be greater than 0.003. So the limits should be greater than 0.003. Clearly, if the minimum limit is reached, then the maximum limit is automatically reached. So what this implies is that we want to ensure that W minimum is greater than 0.003, in which case here we'll consider W min equals 0.003, and then go ahead and find what D has to be. And once we have done that, it will always satisfy the condition that W minimum is always 0.003, or it could be more. It cannot be less than that. So we know that W min is the nominal minus the tolerance, right? If you wanted the positive limit, the max, then you would yeah, almost done. If you want the maximum, you just put the plus sign. So W bar is unknown here. So W min is 0.003. W bar, which is average, is unknown, and 0.01 is the tolerance. So we can solve for W. That comes out to be 0.013. And then finally, the last step is to find D, which now is A plus B plus C minus A minus B plus C plus W. And that comes basically from the same formula, right? A is the sum of B plus C plus D plus W. I just move things around to get D. And so D bar is 0.867, where obviously I use the mean W bar for that W, and then I use the mean values for A, B, and C. And so the answer to part B is 0.867. Okay.